Hi everyone, thanks for tuning into my presentation on Bridging the Chasm, a survey of software engineering practice in scientific programming. This paper is originally written by Tim Storer. I'll be presenting it today. My name is Greg Woodmeyer, and this is for select topics in software engineering for Athabasca University. So some of the things we're going to talk about here: what is software engineering, what is scientific programming, and some more information on the scope of the presentation. So, software engineering. As early as the 1960s, software development projects were experiencing problems, some even calling it as much as a crisis. Projects were considered failures with budgeting for dollars, time, and resources failing to meet projections, resulting in defects, functionality issues, and in some cases, even a full cancellation of the project. So, as a result of this, in the 1970s, the software engineering discipline began, and it's looking to implement fault-free software as requested by a client or customer within the quoted budget and time. In scientific programming, due to the requirements of various sciences, it is necessary to create software to partially or fully simulate experiments and various scenarios to test hypotheses. This is usually the case where it isn't possible to build something capable of performing experiments, say, for example, like the interior of the sun or a black hole or something like that. The developers in scientific programming are typically domain experts without software development backgrounds, so they're self-taught in their domain for the purpose of their research. Adoption of software engineering practices in scientific programming has been slow, or in some cases, as identified in this paper, non-existent. So, the scope of the presentation: this author has completed a detailed survey of software engineering practices in scientific programming, analyzing the details of each in comparison with each other, where some have progressed, where some have failed. Furthermore, the paper is looking at about 3 decades of papers and reporting the problems in scientific programming, and where software engineering practices have and haven't been adopted. So, the problem or motivation identified by the author is a conflict between complex software and the inherent parameters and ability in scientific research and programming to create reproducible and repetitive documented experiments. So I just want to start off with a look at the scientific method. I mean, we've all heard of this through various levels of school. Generally accepted definition of the scientific method is a process of experimentation for the purpose of observing results and answering or realizing hypotheses. Some of the components of that are that theory should be falsifiable, experiments should be repeatable, results should be reproducible, and the experiment and all details should be reportable. So this definition is a little bit oversimplified. There are many more detailed definitions, but this is going to set the stage for the remainder of this presentation. So software and science, why is it important? Some examples of where it's required and where information that we have now wouldn't even be possible without software. Things like CERN's Large Hadron Collider, which is primarily run by software and has, from what I remember, 5 million lines of code, which is the equivalent to some small operating systems. Various Nobel Prizes have been awarded for computer simulations. An example is chemical processes where the cost or complexity would be prohibitive. Climate models for predictions and long-term forecasts require integration of multiple sources of large data sets. Software brings many benefits to science in processing, observing, modeling, and simulating, and all of those need to be consistent in their execution. Large data sets need to be able to be manipulated. It helps when they can be visualized and analyzed for trending and statistical analysis of data. But overall, as mentioned, the primary idea here is that it allows us to do experimentation where primary data collection just isn't feasible. So why, to some, is it considered a problem? So software is subject to bugs. There's no getting around that. And due to the increasing complexity of software for things like scientific purposes, incorrect values can be and are sometimes identified after the results of the paper are published. The unfortunate part here is the invalidation of any future papers that have been cited on this before these results have been, or the issues have been identified. Repeatability becomes difficult due to the many parameters of software, things like operating systems, the actual hardware, virtual machines, runtimes and environments, versioning of some of the dependencies. So if the experiment can't be repeated, the results can't be reproduced. And finally, where results have been invalidated, experiments and hypotheses based on the software are also invalidated. So what is the solution to all this? Practices built in the discipline of software engineering do address many of these concerns. The author identifies a chasm of disparity between software engineering and scientific programming practices. And a direct implant of software engineering practices isn't a silver bullet, but adoption and modification of some of these practices could benefit scientific programming. So in this paper, the author analyzes approximately 200 different papers. There's about 200 citations at the end of it, and the results and the findings that he comes up with can really be broken down into a few categories. The first one is hesitation. So many research teams hesitate to release code as it may lead to the analysis or discovery of a problem with their software, which invalidates the results of what they've worked on and potentially others. Peer code reviews are a pretty common practice in software engineering, however, seldom used in scientific programming. From what I was able to determine here, this isn't an attempt to hide potential issues. The author found that often in highly specialized research, only the domain expert, the lead researcher or the team are actually capable of analyzing the code and interpreting the results to determine if they're actually correct. The domain experts often are also the people doing the programming. Reproducibility. So the author also looks at various journals for their consistency in cataloging submitted code and maintaining the repository of that code. And in about 73% of the articles, they didn't follow the compliance policies that the journal had in place for submitting code to their catalog. And in some of the cases where they were compliant, they often, when the code was downloaded, they weren't able to compile or execute it without error. In a couple of the papers, some authors had looked at trying to gain access to the code at, say, conferences where they would be able to attempt to reproduce an experiment, but came up to many obstacles. In cases where the code was submitted correctly, defects were minimal and non-impactful, and it could be obtained for experimentation. The findings from attempting to reproduce results were also inconsistent. Inconsistency was found to be a result of, for example, the way an operating system rounds off numbers for floating point variables. So even simple things like that. So processes. The author found that processes in scientific programming were similar to the concept of rapid prototyping on software development. The practice involves iteration with a focus on the outputs expected by the domain expert. So taking that iterative focus, that was confirmed through further analysis of research projects and agile-like methodology, although ad hoc in its nature, so not by choice at the beginning of the project. In scientific programming, iterative releases were typically kept internally to the team and released with publications as required for competitive advantage. This was also found within the team where reluctance to share code existed due to the inherent collective ownership that would result. In cases where software development practices were used through outsourcing, the requirements specification was treated by software engineers as complete, while the scientists saw it as an outline that would evolve. So two very contrasting opinions of what that document actually meant. Other papers demonstrated that some scientists preferred self-documenting readable code versus traditional documentation, as this makes code analysis simpler for the domain experts. However, the majority of scientific programming still include detailed documentation, more so than software engineering practices typically prescribe. So the next topic, software teams. Due to the nature of research, teams of graduate doctoral students often change through the life of one of these research projects. The changing of these contributors means that each contributor may understand they're part of the software. However, there's a lack of a primary contributor or owner of the overall product. The length of some projects means that the future contributors could be maintaining legacy systems to continue moving forward with the research. And the last topic here, quality assurance. So, as mentioned earlier, there's a strong reluctance to allow software engineers to review scientific programming code, some stating the results are open to interpretation of quote unquote their model. Software is seen as a means of attaining the results. The software is not the core deliverable of the research, and therefore it cannot get in the way of the science that's being performed. Also, funding in science is based on hypothesis and experimentation, where software engineering has been developed for cost effectiveness on programming projects, among many other parameters. Many scientific experiments requiring software would not benefit from the upfront cost of a lot of what is prescribed through software engineering as best practices. Something I didn't include as a bullet on this slide is testing in scientific programming, which is basically a complete presentation on its own due to the nature of research and the lack of what this author calls a test oracle. The author has contributed a vast amount of work to the study, without much mention about placing more responsibility on the scientists themselves and surveys involving their interest in software development practices. This work has demonstrated the necessity of software throughout many parts of science and research. However, little has been mentioned by him about incorporating software engineering into sciences through things as early as like university coursework. So where this leads to is the adoption of software engineering practices. In order to progress, the author has noted in various parts of the paper where software engineering topics can be adopted in part or modified to fit the practices of scientific programming in a way that adds value to scientific software programming without detracting from the science itself. So software engineering for science programming. Some topics of software engineering that are discussed in the paper make sense. However, further discussion is definitely needed to adapt these ideas in science programming. The first one, component architecture. So it's common to build libraries of objects or components for the purpose of reusability in software engineering. This approach is discussed for science programming. However, with the changing requirements of research, these libraries and components would most likely be in constant revision. Instead, considering something like a service-oriented architecture or like a black box approach, objects would be created like a service where experimental research and verification through code analysis could determine parts of the solution to be correct as they work towards what might be the final exploration or experimentation for their hypothesis. Where services or black boxes would be beneficial in this place is that where a defect is found in a service, they can be corrected, assuming parameters of inputs and outputs remain the same, and the service can be replaced without recompiling the entire solution. This is the same effect in things like where legacy operations are required. The next one is design patterns. So these are one of the least researched topics in this paper and assumably represented in the research field itself. With attempts at design patterns in scientific programming being purpose-built for very specific requirements, which from everything I've read, by definition is not the purpose of a design pattern. The closest example was a paper that discussed a design pattern for simulation, which at a core level appeared very relevant. However, as the simulation grew to niche areas that they're using it for, it definitely became less applicable to use the design patterns that they had created on the outset. Refactoring and reengineering. This topic involves a lot of testing practices, so it's not as well described here. However, it is noted that a concentration is required here to improve carrying forward solutions through a research project where dependencies are constantly changing, things like versions of libraries or components, if that's what is used. The last one, continuous integration. So as will be mentioned in the upcoming slide for conclusions, continuous integration should be a stronger consideration in scientific programming. The problem is the competitive nature of scientific research and the hesitation to release parts of code or publications ahead of the full results, which is discussed more in the next slide. A briefly visited topic that should be front and center is more research on environments, so packaging of code, dependencies, etc., within a portable environment. So when I say that, I'm talking about a virtual machine instead of something like like a Java runtime environment. The portability of Java is desirable in this case. However, as identified by many of the papers, software can be run on a variety of hardware, and surprisingly, will have different outcomes based on the where tolerances are very small, or how variables and parameters are treated. So the conclusions here, is there a silver bullet? And unsurprisingly, the author found through his research that there isn't a proverbial silver bullet, but that both sides, software engineering and scientific programming, need to adapt to the other's practices to find relevance and offer value. Where software engineering tools and practices have been adapted, in part to scientific programming, results have been positive in the outcomes. And the author's citations back up this premise. Although parts of software engineering that are adopted appear to be pretty minuscule, the author could put more emphasis on what the individual parts of this adoption are building towards, or suggest this as a path for future research on the topic. Some tasks for both sides. While programming and science needs to adopt better practices, software engineering practices also need to consider the challenges of scientific programming and adapt to the requirements. Software engineering tools often implement high-level languages requiring code to be interpreted by many layers before finally being processed at a computing hardware, or what some people call a bare metal layer. Each layer through that introduces possibility of defects and errors in translation, or simply cases like rounding of numbers where multiple decimal places are extremely important to the results. Domain-specific languages are promising in this, in addition to the introduction of a capability maturity model in scientific programming. In simple terms, attempting to improve quality assurance through mandating particular practices, or sorry, without mandating particular practices of scientific programming. There's also a perspective here. So the word in the title of this paper, being chasm, is definitely an exaggeration of the state of scientific programming and software engineering. What I found from this paper and the many other papers researched as a part of this is 2 points. Software engineering, or software engineers, have not always had scientific programming code immediately available, and in some papers has created what appears to be an emotional response, presented through things like accusations of poor practices. The second part to this, though, is that scientific programmers are using many of the patterns and practices identified and made standard through software engineering, but they're often not even realizing it, making it more of an ad hoc solution to the problem versus a deliberate implementation of the practice. Code in peer review. So one of the biggest changes that could be made is the standardization and mandatory practice of code review as part of peer review. As the two appear to be independent, or to be dependent, where the code proves the results of the experiment but wouldn't exist without the research requirements, and the research requires the code to demonstrate the hypothesis. If it was mandatory at the outset of the project that the scientific programming code would be under the same scrutiny as the research paper, I think better practices would be inherent, and researchers would necessarily adapt to practices that allow for software to be built without it being the focus of the research. A secondary benefit to that could be stronger consideration for domain-specific languages, where component libraries and foundational code bases could be established for long-term use by various projects. So the slide is just the reference again. And that's it. Thank you for listening.